Okay, guys, let's take a look at today's lesson. We are going to be looking at antiderivatives. We are finally working on integration. Now, some of us are like, yay, because you've needed integration in physics for a very long time and haven't had it. So we're going to look at what integration is. We're going to start with the most simple, antiderivatives. We're just going to talk about antiderivatives. So let's talk about what kind of process it is. When you were in elementary school, you learn how to multiply first, right? I mean, that's just what you do. And then you learn how to divide. These are inverse processes of each other. If I multiply, two numbers together and then I divide them, I'm going to be back where I started, right? But we learn the multiplication first. Like in middle school, you learn how to square things and then square root. If I square 5 and then I square root my result, I'm going to be back to where I started, right? And that is the same kind of concept that we have with differentiation and antidifferentiation. So I take the derivative of something, and then I take the antiderivative of it. I'm back where I started from. Now notice, differentiation we learn first because it's easier. Because I could give you anything, any kind of function, and you would be able to find the derivative, right, with all the rules that we know. I mean, you know how to find the derivative of all different types of things. That is not going to be the case with integration. There will be some integrals that you cannot solve by hand, that you would need an approximation, like that's in your calculator, an approximation technique to be able to solve. Now, I'm not going to give you integrals that you can't solve. That wouldn't be very nice. But I'm saying that unlike derivatives, where we can take the derivative of anything, we can't necessarily take the integral of anything. It is far more restrictive. A lot more rules go with it. Now, in BC calculus, so this is very exciting, probably one of the reasons that you took it, we get to learn all different kinds of integration. In AB calculus, they just learn like 2 things. Okay, we're going to learn like 10. It's going to be fantastic. It's awesome. All right, I am so excited too. It's so great. So what we're going to do is we're going to start with basic integration, and we will learn all different kinds of techniques that will help us to integrate. So let's talk about just basic integration rules or properties. Notice how we really don't have a lot. We have 2 things that we can do. That's it. And we need to realize it's highly restrictive. We can split apart by plus and minus. That's okay. Okay, that's fine. And we can pull a constant out. That's it. Okay, without a rule. It's very rule-based. A lot of students want to try to do some kind of reversal product rule. There is no such thing. The closest we get to it is integration by parts, which we won't talk about until after the break, like in January or something. We'll talk about other types of integration techniques. So just know that we are very limited in the normal kinds of rules that we can do. Unlike limit rules, they're so flexible, and a lot of derivative rules, we don't have that going on here. We can only take the integral of things that are being added and subtracted separately and pull a constant out. That's all we have. All right, so let's talk about how antiderivatives relate to integration. Basically, the process of taking antiderivatives is called integration. I mean, that's the process of that. And what we're going to be working with at first is called indefinite integration. Indefinite integration. That means that I don't have numbers here on my integral sign. You've probably seen that in your calculator. I know we worked with it a little bit last year, where you would have numbers, a lower bound and an upper bound on your integration side. That's called definite integration, and we will get to that. Right now, the very first thing we're going to talk about is indefinite integration. That's where I don't have numbers on my integral sign. And so here's how it would be written. The integral is typically written like this. We have an integration sign, and then of f of x dx. Let's talk about the dx part. When we are taking derivatives, we do like dy dx. Remember, the dx meant we took the derivative with respect to x. Well, it has the same kind of meaning with integration. It's telling us which variable to integrate. Now, in Cal 1 and Cal 2, many students are like, why do we need that? Well, in Cal 1 and Cal 2, we only work with one variable, so it's just kind of there, and we're not seeing the importance of it. In Cal 3, where you deal with multiple variables in an integral, it tells you the order to integrate them in, or which, do partial integration. So this is very important. We need to have it. It tells us which variable that we're working with. Okay, that's all it does. So we would integrate a function f of x with respect to x, and that's going to equal, and they like to capitalize the antiderivative. For whatever reason, that's just a typical procedure. They capitalize it, and this little guy, the plus c, it causes students much pain. It's just such a little guy right there. If you don't put the plus c, you're going to lose a point. Okay, on the AP test, if you don't put the plus c, many times you're going to lose the point. So it's very important. A student was talking just earlier this week. One of my previous students was like, I lost 17 points because I didn't put a plus c. Now, of course, that wasn't on one assessment. That was over a lot of assessments. But that's a lot of points, especially on an AP scale. So we need to be sure to write plus c. And some students will just write it on the top of their paper. Their quiz, just plus c, plus c. And you'll see when we work on the daily work why that's a problem. So let's talk about why. Why do we need a plus c? Okay, let's look at this example. Let's say I had x squared plus 3. All right, let's say that was my function, and let's say I want to take the derivative of it. That would be 2x, right? That's the derivative. Now, if I integrate this first derivative, I'm going to get back to here. But notice, I don't have anything that represents the 3. Right? So when I take the integral of this, I get back here, but I don't know what was here originally. I would just be given this. This, I would do my reversal power rule, which we're getting ready to learn. I might as well just demonstrate it on this. Reversal power rule is this right here. And basically, it's reverse of what? So what did we do here? We brought the exponent down, and we subtracted 1. That's the power rule. To do the reverse of that, we're going to add 1 to the exponent and divide by that. Okay? I'm going to add 1 to the 1 and get 2 and divide by 2, and that puts me right back here. But I would have to put a plus c because I don't know what might have been there. If I had this as my function, wouldn't I have the same derivative? Do you see the importance of the c? C could be anything. If you don't put it, then what are you saying c was? 0. And that's one of an infinite number of possibilities. So what you've done when you don't put the c is you're like, well, I know it was 0. I don't need a c. And we don't necessarily know that. So we have to put that when we integrate. That's why I look at this table. All of their integrals, their indefinite integrals, have a plus c on them. That would be why. Because we don't know what constant there could have been. All right, I think that's enough lecture about c. Hopefully we will remember to put the plus c. Yes. I'm demonstrating that what would the derivative of this one be? It would be the same thing. So if I'm going to, and I'm not doing the antiderivative part, I haven't done that. If I were going to take the antiderivative of either of these, I would get x squared plus c because I don't know what was there. Right, when we do the antiderivative. I just haven't really done one yet. I talked about doing one. Okay? So you would write plus c because we don't know what it is. All right. So let's, this is kind of written kind of weird, I think. But if this piece right here gives you your, I call it the reversal power rule. I don't even know. It probably has some name. I don't even know. It's a power rule, but it's in reverse. So what I do is I add 1 to the exponent, and I divide by that new exponent. That's the reversal power rule. Okay, that's all it is. I add 1 to the exponent and divide by, so there's my exponent. I add 1 to it and divide by that, and then that's my antiderivative. Now, as far as memorizing all of these new integral trig, you can if you want to. What I prefer to do is stick with what I know And I like to think to myself, okay, if I were to take the derivative of something and get cosine, what would it have been? That's what I think in my head. It would have been sine, so that I don't have to memorize a whole new set. Because typically what students will get confused with are the signs. They get them mixed up with sine and cosine. So just be careful. All right, if you want to memorize this whole set of integrals, you can. Or if you want to do, like I was saying, what I do, just remember it from the derivative part and go backwards. All of that. So here's our friend. We know, we identify. We like that guy, right? So nice. Isn't the integral of e to the x is e to the x? So nice. Well, yeah, plus c. So this guy right here has already caused problems in the earlier class. I want you to take special note of it. If I integrate 1 over x or 5 over x or 7 over x, I'm going to get whatever that constant was, 5, L in absolute value x. That's what I'm going to get. I'm not going to do the reversal power rule on that. This does not do the reversal power rule when I'm to the 1 over x. That is the derivative of L in x is 1 over x. So the integral of 1 over x is L in x. Okay, so just make note of that because we had some issues earlier. And remember I was talking about how much the integral guys love the arc functions? Here we go. Integral of 1 over 1 plus x squared is arctangent. Okay, so just so that you're familiar. All right, any questions in general? We're going to do some problems. Any questions in general? Yes. They're trying to force this to look like this. They're trying to demonstrate that that these are reversed properties. That's all. It's the same thing. They're just trying to, and that's why this is written really weird. They're trying to demonstrate that they're reverse processes is all. Right. Right. Yeah, and that's how I remember it. I don't remember it like this. Yeah. Anything else that we need to discuss before we do some problems? Okay. Let's do some problems. It went too crazy. Okay. All right. So let's take a look at our first one. We have some multiplication going on, and some students will want to take the antiderivative of them separately, and that is a big no-no. Okay? We don't have a product rule in integration, period. So we have to work around it. So we've got to actually multiply it out. We really do. Now we're going to learn U substitution. That's like the next thing. And you can use U substitution with some types of multiplication, but it's a beautiful process. But we really don't want to go there if we have something simpler to do, like just multiplying it out. So that's what we're going to do. We're just going to multiply it out, and then we're going to take the integral piece by piece because they're separated by pluses and minuses. Right, that's the only thing we have going for us is if it's pluses and minuses, we can do them independently. So let's do that. Let's first go ahead and just multiply it out. So that gives us 2x squared plus 5x minus 3. Now the very proper way to write it is this is called the integrand, is to put the integrand in parentheses with the dx or whatever variable dy, whatever's out there. Now, if you forget to put parentheses, I'm not going to have a heart attack. It's okay. Now some professors would have a heart attack, okay, if you don't put the parentheses. But for me, I just determine if it's in front of the dx, I know it's part of my integrand. And if you want to do that, you can as well. Just be cautious. Know that that would be the proper way to do it, is to put it in parentheses. Now, I'm not going to separate them out like integral of 2x squared plus integral of 5x plus, minus. I'm not going to do that. We're just going to do that in our head, just knowing that we can do the integration separately. So let's do our reversal power rule. So we add 1 to the 2 and get 3. And then we divide by 3. So this is 2/3 x cubed. And when you first start working the reversal power rule, you might want to just check it. if I take the derivative of this, am I going to get that? That's what you should be asking yourself if you're unsure whether you did it right or not. So if I take the derivative of this, that's going to give me 2x squared. So I've done it correctly. Okay, so just I encourage you to check. So here, plus the add 1 to the 1, I get 2. So and divide by 2. And then the minus 3, that's going to be minus 3x, and then my plus c. So there's my antiderivative. Okay, our very first antiderivative. How are we doing? Yay! Not too bad, right? Okay. Now, I had a question earlier today on, you know how we have to do second derivatives and third derivatives? Are we going to have to do like second integrals and third integrals? And the question, that answer to that is yes, but it's not going to look like you think it would. There's not going to be like an integral sign with a 2 on it or something. It's basically going to be a problem kind of like this one or this one. And we'll talk about, and actually this one isn't, but this one and this one right here are going to require us to do more than one antiderivative. All right, so first let's talk about what it means by solve the differential equation. We do have a unit on differential equations that comes up later, but I want you to get used to the way, the terminology. And first of all, we got to figure out what is a differential equation. Well, it's an equation that has derivatives in it, right? Differential equation that has derivatives in it. It could have more than one derivative in it. It can be crazy looking. All right, we're not going to deal with crazy. So, solve the differential equation. What that means is you have something with a derivative in it, and the solution would be the original function. That's what it means. Solve the differential equation. That means, what did this originate from? What is my original function? That's what it means. So, if they give us a second derivative, and they want us to solve the differential equation, what are they telling us to do? Yeah, find f of x, right, or f. We're going to have to go backwards twice, right? We're going to have to go backwards twice. And so we're going to have to do an antiderivative to get us to the first derivative, and then another antiderivative to get us to the position. So we are having to do more than one. It's just would be written something like this. Now, when we do an antiderivative, we get a plus c. Sometimes they give us enough information to find c, and sometimes they don't. If you look at this, what do you think these values are here for? To find c, right? They give us some like first derivative values and function values so that we can find c. Here, they want us to find f, but we don't have any values. So we are going to have to do the same process we're doing here, but we're not going to be able to find c. Okay, does that make sense? You with me? So if they give you this, that means you have to find c. It's not like an option. Like, oh, I don't, I see those things there. I just don't want to mess with them. It's not kind of like that. If you see those, that means find c. All right, they're not going to tell you. You'll just have to know. So let's start this. We're going to solve the differential equation. We're going to do that by doing two antiderivatives. My first antiderivative. So here's how I think of trig. I think, what would I have taken the derivative of to get a cosine? That's what I think. What would I have taken the derivative of to get a cosine? Would have been a sine, right? So I would have sine x plus c. And so I encourage you to stop and find c right now. Don't wait until the end. Much more difficult, so stop. So here it tells me that when x is 0, my y value is 3. So 3 equals sine 0 plus c. What is sine of 0? 0. So c is 3. So my actual first derivative is sine x plus 3. Okay, we okay with that? Yes. When they're very nice to us and give it to us at 0, you don't have to show this work if that's what you're asking. No, you don't have to show it. You can go straight to the answer. I'm just showing you how I got it. Okay? All right. So now we're going to go backwards one more time because we want the actual original equation. So f of x, so I think to myself, what would I have taken the derivative of to get a positive sign? A negative cosine. So it's negative cosine x, And then the antiderivative of 3 would be 3x plus c. And I, again, are going to use this piece of information right here. When x is 0, y is negative 2. Okay. Now here's where it would be a little dangerous to think of it as the y-intercept, because actually cosine of 0 is something. It's not 0, right? So cosine of 0 is 1. So I have negative 2 equals minus 1 plus c. So c is a negative 1. So f of x is going to be negative cosine x plus 3x minus 1. And that's the solution to our differential equation. Okay, is that okay? Okay. Our next problem. Now just know from here on out, we're going to be using a combination of derivatives and integrals. We're not going to just integrate. We're going to be doing both. So that causes some students to get a little confused about which way they're going, forward or backward. So just want you to know right now that you're going to have to be able to do both. All right, so here we have a particle moving along x-axis at a velocity of, we have our first derivative velocity function. At time t equals 2, its position is x equals 3. What do you think they gave us that information for? To find c. Okay. The first question is find the acceleration. Does that involve anything that we've learned today? No, it just is derivative, right? That's it. Just derivative. So acceleration, a of t, is going to be 12t minus 6t, and they just want us to find it. Oops, 12t squared minus 6t. So, okay, we found it. That was nice. Now they want us to find the position function. Okay, we're going to do the antiderivative of the first, of velocity. So, and I will tell you that the typical naming of it is x of t. For positions, they like using x of t when we're dealing with acceleration and velocity. Velocity is v of t, acceleration is a of t, and position is x of t. That's just tradition, what they like to use. So, just so you know. So we're going here. We're going to add 1 to the 3, which gives us a 4, and we're going to divide by 4. So that's t to the 4th. Add 1 to the 2, gives us 3. Divide by 3. That gives us, look how pretty that's cleaning up. Again, if you're worried that you're doing it wrong, I encourage you to do the derivative and see if that's what you get. Plus 5t plus c. So now we have this information at time t equals 2. The position is x equals 3. All right, so 3 equals 2 to the 4th minus 2 cubed plus 5 times 2 plus c. So we do all of our beautiful arithmetic, and we get c equals negative 15. So then our position, x of t, is going to be t to the 4th minus t cubed plus 5t minus 15. Okay? All right, our very last one. We have the second derivative, and we're asked to find the position. What does that mean to us? What are we going to have to do? Antiderivative twice. Okay, that's what that means. Antiderivative twice. So let's do that. So f prime of x. Okay, so the antiderivative of 1 would be x. All right, now we're going to have fun with fractions. We love fractions, yay. So we add 1 to 4/5, and we get 9/5. And dividing by 9/5 would be the same thing as multiplying by 5/9. So it's going to be 5/9 x to the 9/5 plus c. Don't forget your plus c. Are we all right with that? Okay. All right. Now, we don't know. They don't give us any information on finding c, so we're just going to have to just keep pushing forward. Just carry the c with us. So f of x. All right, so x, so I would add 1 to 1 and get 2 and divide by 2. That's x squared. Now this one's going to be a bit messier. I'm going to just put the 5/9. That's a constant that's just going to be hanging out there for a minute. So I add 1 to 9/5. I get what? 14/5. So that means I have to multiply by 5/14. X to the 14/5. Plus, and what do you think the antiderivative of c is? Cx. And when we have used up c, we just go to the next alpha letter, d. So plus d. So now it's just a matter of prettying up this poor little guy right here. So I have 1/2 x squared plus 25 over, what was that, 126 x to the 14/5 plus cx plus d. And I know it's troubling that we don't know what c and d are, but sometimes we just can't know everything, right? We just can't know. All right, any questions?